Good day everyone. We will discuss about memory on this video. Let's start with 32 and 64-bit operating system. 32 or 64-bit that we are referring to are the bits that can be used for addressing the address space. For example, a 32-bit CPU can address only 2 power 32 byte of memory, which is 4 GB. Servers that are running a 32-bit operating system have 4 GB of total virtual address space, which is called VAS, which is divided evenly by default into 2 GB of kernel mode VAS and 2 GB of user mode VAS. Applications can only allocate memory from user mode VAS, which significantly limits their ability to access memory in a 32-bit process. If an application is compiled with large address-aware flag, like SQL Server is, it can address memory beyond 2 GB through the use of two different options available in Windows Server. The first option is /3 GB or 3 gigabyte tuning option that exists to change the VAS split from being 50-50 to being 25-75 for kernel mode and user mode VAS. Basically, you take 1 GB away from the kernel and give it to the user mode processors, allowing them to make use of more memory, but only up to 3 GB. The other option is address windowing extension or AWE, which leverage page address extension to make use of 36-bit pointer instead of a 32-bit pointer, allowing you to access memory beyond 4 GB up to a maximum of 64 GB. This requires using memory through page table entries in the kernel to map the address spaces above 4 GB. If you make use of /3 GB tuning, this restricts the available PTE such that the maximum amount of addressable memory is limited to 16 GB. A 64-bit process has 16 hexabytes of calculated user mode address space. But since this is beyond any reasonable amount of memory, it is limited by 64-bit operating systems to 24 terabyte for latest operating systems, which is still well beyond the limits of any physical server's configured RAM. This allows SQL Server to allocate all of the memory on a 64-bit server without any special configuration, since calls to virtual alloc have to be backed by user mode VAS. A byproduct of this is that all of the memory allocated by calls to virtual alloc is pageable by Windows. So if it thinks it is in memory pressure, that is the operating system, it can page out the entire SQL Server process, resulting in significant impact to performance. Because of this, 64-bit servers can leverage the AWE API calls that are previously needed under a 32-bit process to prevent paging of the process by using lock pages in memory to lock the pages from the OS being able to page them. This is very specifically locking pages and not AWE. The underlying Win32 API call happens to be the same. Allocate user physical pages, but it does not require enabling AWE on a 64-bit server. It just requires the lock pages in memory user right assignment in the local security policy. 32-bit is kind of obsolete now, so my videos on memory will focus only on 64-bit. Let's discuss on physical and virtual memory. Consider I have a 4 GB server. That is a server that has got 4 GB of memory. Out of this, let's consider 2 GB is utilized by operating system and the device drivers, and rest 2 GB is for the application use. A developer cannot make direct physical memory allocation by writing an instruction to make memory allocation directly on the physical memory. There is high possibility some other application can override that, causing issues if physical memory allocations were allowed to applications directly. For example, we cannot make physical memory allocation like, let's consider 2 to 2.5 GB is for VLC player, 2.5 GB to 3 GB is for Edge browser, 3 to 4 GB is for SQL Server, as we may not know how many applications will be installed on the server, and not all applications can have direct physical memory allocation reserved. Also, getting a continuous chunk of physical memory is not practically possible. What Windows or any other operating system does is it provides empty address space for all the applications. Since our example is on a server with 4 GB physical memory, Windows will basically advise applications that each application has a 4 GB of virtual address space. Now, whatever memory allocation the application has to do, it will utilize the VAS, and OS will take care of the address translation for these virtual address to physical address that is on the physical memory. That is the physical address that I'm referring here is basically the physical memory. For example, let's say application 1 allocates address 100 and application 2 again allocates address 100. So just to understand, each and every application will be getting its own VAS. Yeah. So remember, these are all virtual address space, and also each application will get 4 GB VAS as the available memory is close to 4 GB. But the operating system will translate the physical memory for application to example address XYZ, and for application 2 to address ABC. Consider this is my virtual address space and this is my physical memory. So the Windows operating system uses a page translation table to perform the virtual to physical address translation. Let's consider when we allocate a 4 KB page on the VAS, and let's assume, for example, this address, this is at the address X008. Windows will capture this info on the page translation table that VAS address X008 from process R has physical memory allocation at address X023. And this is captured in the page translation table, as you can see here. Moving on. Going back to our example of 4 GB VAS, where 2 GB is taken by the operating system and 2 GB is utilized by your user process. We know that the server has 4 GB physical memory, and we also have a page file which is considered to be an extension of our physical memory. This page file will be placed on your disk subsystem. Let's consider Chrome uses close to 700 MB memory, and then Outlook uses another 800 MB memory. Now let's consider VLC player is requesting 1 GB of memory as it needs to play a huge movie. In this case, Windows using LRU method, that is the least recently used method, will move some of the pages of Chrome and Outlook to the page file, and then it allows the VLC player to utilize the requested 1 GB memory. Now let's say we stop the video and then open Chrome to browse something. In that case, Windows will basically move the required pages for Chrome, and if those pages are on page file, it basically brings it back from the page file to the memory. This is the reason we call page file as an extension of physical memory. So now, how much VAS do you have on the database server or on any particular server? It will be an amount of memory plus the page file. The amount of VAS you can have is the amount of memory plus the amount of page file. That's it for this video. We will continue discussing on memory on our next video. Thanks for watching. Have a great day. Jai Hind.